In this video, we're going to go through the solution to problem number 3 from the 1988 AP Physics C Electricity and Magnetism AP exam. We're given a long solenoid, and in part A, we need to apply Ampere's law to find the expression for the an expression for the magnetic field near the center of the solenoid. And they're really nice to us this time. They even give us the Amperian loop to use. If they weren't being so nice, they wouldn't have done that. They would have just said, derive an expression for the magnetic field at the center of the solenoid, and half of the students probably would have tried to derive it directly using the Biot-Savart law and then adding up a whole bunch of equations, and then they would have spent all 45 minutes on just part A of the problem. But here they told us an Amperian loop to use and told us to use Ampere's law. So we use Ampere's law. There it is. And with this Amperian loop, there are a number of things to keep in mind. First of all, with the right-hand rule, you can recognize that going from A to B, that actually is going to be in the direction of the magnetic field here. And C to D, well, there is a very small, pretty much negligible magnetic field outside of it. They tell us it's a long solenoid. Long means ideal, which means there is going to be zero magnetic field outside of the solenoid. So the path going from C to D is not going to have any magnetic field in it. And the path going from B to C and the path going from D to A, those paths, well, once you get inside the solenoid, yeah, there is magnetic field here. But look at that B vector dot ds vector. The magnetic field's pointing toward the right, but B to C and D to A are pointing up or down. That's perpendicular, so dot product of two perpendicular vectors is 0. So we recognize that those parts give 0 contribution. So the only non-zero part of the contour integral is going from A to B. So that means the left side integral of b vector dot ds vector is just the integral from x equals a to b of b times dx. Well, technically b vector dot dx vector, but we took that into account when we plugged in our boundaries here, from x equals a to b. Now, b is constant there, so that comes out, and the result of that integral is just going to be b minus a. So the result, therefore, is just BH, because B minus A, that distance, is given here as H. Yeah, be careful to put your final answer in terms of the given variables. So BH is equal to mu naught times the amount of enclosed current. Well, how much enclosed current is there? The amount of enclosed current is given by, well, each of these wires has an amount of current little I in it, so to speak, because essentially with the solenoid we're dealing with a bunch of rings here. So and we're told that there are n rings per unit length, so that means that the amount of current per unit length is going to be IN, so the total amount of current is going to be IN times H. Oh, there's an H in the numerator, there's an H in the denominator, that's nice, the H's cancel, so B equals mu naught IN. The points here were distributed for 1 point indicating Ampere's law correctly, 1 point for dividing that up into a bunch of contour integrals. In our case, we simply said that 3 of those contour integrals were 0, and the only one that was not 0 was the part going from A to B, so I wrote it like that, and in fact, it looks to me like they might have given that point simply for the answer there. BH. 1 point for recognizing that the enclosed current is NIH, and 1 point for the correct final answer. So 4 points for part A. For part B and C, we're saying that we now have a little ring of radius R2 placed at the center, and current in the solenoid is decreased at a steady rate, and in terms of the quantities, determine the EMF induced in the loop and the magnitude of the electric field in the loop. So we have loop of radius R2, and we're going to use Faraday's law here. Faraday's law is that the induced EMF is negative d phi dt, where phi is the magnetic flux given by A vector dot B vector. Well, A vector can point either toward the left or toward the right, however you want it, but we don't really care in this case since they're asking for the magnitude anyway. and B vector is definitely pointing toward the right. So we can just factor out the A because the area of the ring doesn't change. The only thing that changes is the magnetic field going through it. And how's that? Well, we have a d dt of mu naught I n. So that's the magnetic field that we got in part A. Well, mu naught, of course, is constant. N is constant, so that comes out. So what we're left with is negative A mu naught n times di dt. Now, what is di dt? We're told that the current is changed at a steady rate, which means that di dt becomes a delta I over delta t, because we're told that this happens over a time of t. So delta I, well, we started off with no current, and we end with current, and we start off with time 0 and end at time t, so we just plug those numbers directly in. And actually, let me change something here. We started off with current, and we end with no current, because it's decreased at a steady rate from I to 0 in time t. So that's why we got a minus sign here, because our final current was 0, initial current was I, so delta I was negative I, delta t was just t, and the negatives cancel. The area of the ring is pi r2 squared. Got to plug that in, don't just leave it in terms of A. So there's our final answer for the induced EMF. And part C, the magnitude of the induced electric field at a point in the loop. Well, let's see now. We know something about electric fields and potential differences. The magnitude of the potential difference is equal to the integral of the magnitude of the electric field that's there. Notice that I did not put in a minus sign because we're interested in magnitudes here. And since this is happening at a steady rate, and also, more importantly, the electric field is going to be constant everywhere in this loop if it's a constant geometry, constant resistivity loop. We get that coming out of the integral. So the integral of ds is just s, but that s is 2 pi r2, where r2 again is the radius of our loop. So therefore, solving for E, divide both sides by 2 pi r2, and plugging in the induced EMF that we got from part B, and working out a few terms, canceling some pi's, that sort of thing, we get our final expression that the magnitude of the electric field at any point in the loop is mu naught Ni R2 over 2t. Now, the way the points were distributed here back in part B was worth 4 points. 1 point was for writing Faraday's law, which we did back on the previous slide. 1 point was for correctly plugging in the magnetic flux, which we did in the end when we plugged in the area, and also earlier on when we plugged in the field back in the previous slide. 1 point for the correct expression of dB dt and evaluating that like this, and then 1 point for the correct final answer. With part C, the points were distributed such that there were 3. 1 was for the statement of this integral. They actually wanted it as a vector contour integral, and I think that in this case maybe they would have given the point. It's kind of hard to say, but they did prefer the vector contour integral. At least that's what they gave in the official solution. I think this is fine because of the fact that we're going from one point to another, and we had already dealt with a vector type of situation here. But anyway, they also gave a point for evaluating this as E times 2 pi r2, and then a point for the final correct reduced answer. Now, moving on to part D and E. So we get rid of the little loop, and now we make it a big loop. And they want the induced EMF in the big loop and the magnitude of the induced electric field at a point in the big loop. Notice that the big loop is surrounding our solenoid. So the EMF induced in the loop. So in this case, the flux only goes out to R1. So that's all we care about in this situation. In other words, it has absolutely nothing to do with R3. The area through which the magnetic field exists is just the area of the solenoid, which is pi r1 squared. So that's the magnetic flux expression. So again, our Faraday's law, and factoring out that area which doesn't change, but the magnetic field does change in accordance with the expression that we had in part A, we get, just like we had in part B, this di dt is just negative I over t, and we get our EMF as pi r1 squared mu naught ni over t. The points here, there were 2 points, one for basically the Faraday's law statement with the plugging in of the correct expression here, and 1 point for the final answer. And part E, determining the magnitude of the induced electric field at a point in the loop. Well, this is where we actually do care about the radius of the loop, because that delta V is the integral over the entire loop. And the electric field there is constant, so we get an S, but that S is actually the circumference of the loop, 2 pi r3. So therefore our electric field is this script E, which was what we just got in part D, divided by 2 pi r3, which reduced becomes mu naught ni r1 squared over 2 r3t. The points here were given 1 point for getting that Faraday's law, that the EMF ended up being E times 2 pi r3, and 1 point for applying Faraday's law, and not Faraday's law, but 1 point for plugging in the result that we got from Faraday's law in part D, and then reducing that for the electric field. So if you have any questions on any of this, please let me know. That's the solution to problem number 3 of 1988 AP Physics C, E, and M. Thank you.